So more reductions, more undecidable languages. So remember, our classic undecidable language is ATM, and this is the set of these pairs where the first component of the pair is the description of a Turing machine, and the second one is a string W that gets fed into M, and M accepts W. Okay? And from that, we reduced ATM to a couple of other languages last time. What did we do? We did halt. That's the set of MW such that M halts on W. Okay? So we reduced ATM to this, and since ATM is known to be undecidable, that implies that this is undecidable. We also reduced we also then did one that was not in the book. So this is in the book. And then one that's not in the book, I think I called it acirc. It's the set of descriptions of Turing machines such that M accepts W if and only if M accepts W circulated, i.e. W rotated by one position. Okay. And this was a more complex, this reduction, the mechanics of the reduction of ATM to halt was fairly straightforward, but the mechanics of ATM to this language was more complicated. And but if you understand this, then the homework problem, which is, I don't know, I'm not sure that's what it's called, M such that M accepts W if and only if M accepts its reverse. This is a homework problem, and you can solve this in a way that's similar to what I showed you for this one. So the reduction of ATM to this is similar to the reduction of ATM to that. Okay? That's why we did this one in detail, because I think if you just had this, if you just saw this problem on your homework without having seen something like that, it would really be too hard. Okay. Now let's do some more. ETM, that's M such that M is a Turing machine, and L of M is equal to the empty set. Okay? So ETM here, the E stands for empty. So this is just saying M is a Turing, this is the language of all descriptions of Turing machines such that each of those Turing machines only accepts the empty language. Okay? So you'd think you think that would be decidable. I mean, when I first, I don't know. I mean, after you get some intuition, almost everything is undecidable. But this is the empty language. I mean, it's you're basically saying the Turing machine doesn't do anything. This Turing machine M just rejects everything, or not rejects, but rejects or doesn't halt. It's, you think you could just look at the innards of a Turing machine and decide that. Again, taking the analogy of that you're a candy machine mechanic, and you get to look at at candy machines, maybe ones you've never seen before, but you don't test them by seeing whether they work on the Mars bars. You have to actually look at the innards of the machine and decide if they work or not. And here we're asking, is this a machine that never works? It never gives candy, ever. It's always just sort of sits there and does nothing. Or maybe it doesn't just sit there. It whirls and makes noises and smoke and so on, and it steals your money. But in the end, it doesn't give you anything. Okay, you'd think you could, the candy machine mechanics should be able to recognize those machines. It's not a very subtle question. But what this is saying is, no, ATM is undecidable. There's no Turing machine that can take in an arbitrary description of another Turing machine and decide whether or not, maybe it's the not part that makes it more difficult, whether or not that Turing machine just accepts the empty language. Okay, so let's do the proof of that. Okay, suppose R is a Turing machine that decides ETM. Okay, so we're supposing that ETM is decidable for contradiction purposes. And that means that there is a Turing machine R that actually decides that language. Okay? Now we're going to use that Turing machine. We're going to use the supposed existence of this Turing machine R to build another Turing machine which can decide, in this case, ATM. So actually we're going to reduce ATM to ETM. Well, what does that mean? That means we will use the supposed existence of R to describe a Turing machine H that decides ATM. Okay, that's what a reduction means. Okay, so what is this Turing machine H? How does that work? So first of all, what does H take in? What's the input to H? A what? A Turing machine and a string. Okay, because H, I'm just sort of setting up the thing here. H is supposed to be a Turing machine that will decide ATM. So H has got to be taking in the input that a Turing machine that decides ATM would do. I mean, the input to ATM, or the elements in that language ATM, are a Turing machine and a string, pairs like that. So H, I think it's helpful when you're setting up these reductions or trying to think about these reductions, is to see the big picture first of what you're trying to do, and then you can fill in the details. So this is H, and it decides ATM, or it would decide ATM if R exists. And so it takes in input of that form, MW. And inside it, it has R. Okay? It has this supposed Turing machine R that can decide ETM. And now we want to put in all the other innards in here so that an accept out of R is an accept for MW, and a reject out of R is a reject for MW. So all that's left is to fill in this other stuff here. Okay, what actually goes on in here so that we can use this supposed R to do this wondrous thing about creating a Turing machine H that decides ATM. Okay, so that's the heart. I mean, this kind of picture, when you're posed with this problem, when you're posed with the question of show a reduction of ATM to some new language, you should be able to automatically write this kind of picture, just to organize your thoughts, organize what you're trying to do. And then, of course, all the hard work goes into here. But if you haven't even gotten to this point, then you're just, you just don't know, how to begin. Okay, so what does H do? Well, I haven't left myself enough room, so I'll just tell you the details down here. Okay, so what H does, remember, H is taking an M and W. Okay. So it creates on its tape, or writes on its tape, the description of a Turing machine, let's call it M1. Oh, where's my magic chalk? There. Turing machine, which in fact is identical to M, except for one addition. That the first thing it does, it first checks if the input to M is W. Remember the sequence of events here. H is a Turing machine which is going to be able to take in an arbitrary pair MW. But having taken it in, it knows what M is, it knows what W it is. So what you want in here is the machinery to then create on its tape a description of a Turing machine M1, which does the same thing as M, except first it checks if the input to M is W. It has W in its hand at this moment. So we have the possibility of actually creating this Turing machine M1, which checks for the specific W. This is the specific W here that was fed in, that's going to be fed into this H. Okay? So whenever an MW gets fed into H, this is what H does. It creates this Turing machine, which now has built in the check whether the input is, the input, I guess, to, this should be M1, whether the input to M1 is W or not. Okay, that's that specific W. Okay. Now, if the input is not W, then M1 rejects. That's what M1 should do if the input is not W. Okay. But if the input is W, okay, this is the input to M1, okay, then we're still describing what H is doing in here, it's creating this Turing machine M1. And the Turing machine M1 is identical to M, except that the first thing it does is it looks at W, and if it looks at its input, and if its input is not W, then it rejects. Okay? So, but if the input to M1 is W, then H uses R. We haven't used this guy yet. It uses R to decide if L of M1 is empty. Okay? That's what we said. There's a Turing machine that can decide ETM, and that means that Turing machine can take in an arbitrary Turing machine, description of a Turing machine, and decide if the language that accepted by that Turing machine is empty. Okay? So what's happening here is when H sees a particular M and a W, it's cooking up a description of a Turing machine M1. That Turing machine M1 is the same as M, except that it first checks whether the input is W. Okay? And if it is not W, it just rejects. Okay? But if it is W, then it's going to feed M1, description of M1, to R. Okay? So when, yeah, right. So this M1, what is its language? Tell me something about its language. Okay, what possibly is in the language of M1 at this? Given what we have here, what could possibly be in the language of M1? Yeah. What? Just W, yeah. The only possibility for LM1 is W. Now, it doesn't necessarily have W in it, but it certainly can't have anything else. Okay? By construction, the language of M1 is either empty or it's just W. Because M1 is built to reject everything other than W. Right? When it's, it rejects it first, and otherwise it takes in that W and runs on it. This is identical to W. M1 is identical to M, except that it first does this check to see that the input is W. Okay? But now R, what does R do? R looks at M1 and decides whether the language of M1 is empty. Okay? If the language of M1 is empty, what does that mean in terms of M? Hey, what? Yeah, right. LM1 is empty if and only if M rejects W. Okay? And LM1 is not empty because, well, if and only if M accepts W. So if we have this Turing machine R that can decide whether the language of another Turing machine is empty or not, when H cooks up this Turing machine M1 and feeds it to R, the result from R, accept or reject, is used to see whether or not M accepts W. So, yeah, reject, oops. Okay, so we've got to make sure we get the accept and reject correctly here. So we've derived that the language of M1 is empty if and only if M rejects W. Okay, so that when R sees that LM1 is empty, is that an accept or reject from R? It's an accept, right, because of the way this is constructed. Okay, that's an accept for R. So when R accepts, we want to report a reject because that means that M rejects W. And looking at here, we see that when L of M1 is not empty, okay, that's a reject by R. R rejects its input M1. Okay, but that means that M accepts W. So whenever R here says a reject of its input, then we want to report an accept that M accepts W. Okay? I hope that you're getting the game plan at this point, because now we've seen a few of these constructions. And actually, this one is not that hard. The innards of this is just not that hard. It's a puzzle always to figure out how do you want to use your magical Turing machine, your supposed Turing machine here, to be able to solve a problem that you already know is undecidable. And so it's kind of a recoding. How do you massage the input MW? How does some Turing machine H deal with MW to create another Turing machine M1 so that when R looks at M1, what it decides, reject or accept, can be used to accept or reject that input? There's always these little puzzles. Okay. So the consequence is that now we've described this H that can do this. Now you have to be clear on who's doing what. Okay, we, the humans, are describing how what H looks like. But inside, we also have to prove that really this creation of a Turing machine M1 and so on is something that a Turing machine can do, because H is a Turing machine. So you have to feel convinced that there's a Turing machine that can take in an MW and create a description of a Turing machine M1, which is identical to M. Well, that's certainly simple because it can just copy M here. But in front of what M does, before M begins its work, M1 begins its work, it has to check first that the input is the specific W. Well, the specific W comes into, H sees what the specific W is, so H creates this description of a computation, a Turing machine, that can just look at the input and decide whether or not it's that specific W. Well, we know how to do that even with a finite state machine. So certainly a Turing machine can create the description of a finite state machine that looks at a particular string, looks at an input string, and decides if it's that particular string W. So that's no big deal. So you should, at this point, without even seeing all the specific transition rules and low-level details, feel confident that H, a Turing machine, can do all of this. But we're the humans, we're just describing what H does. And so we aren't creating M1. H has to create M1. What we're doing is arguing that there is such an H that can create M1. Any questions on this? Okay, so this one, deciding whether it's empty, is undecidable. And now let me give you another one. QTM is empty if and only if, no, sorry. I'm going to describe the language. This one is two Turing machines. So the input to this language, or the strings that are contained in this language are two Turing machines, and descriptions of two Turing machines, and I guess I'll leave it like that, such that L M1 equals L M2. So this is the equivalence. The EQ stands for equivalence or equality. Are the languages that are recognized by M1 and M2, are they the same? Now this is a very practical problem, and this is a problem that people would really like to have a decider for, because this means one person writes a program that's supposed to do a particular thing. Another person writes a program that's supposed to do that same particular thing. Those programs are not going to be identical unless somebody copied from somebody else. Okay. They may even have totally different ideas or different algorithms behind them. But certainly as programs, they're not going to be the same. But you'd like to know, do they compute the same things? Do they accept the same languages? Now, we're using this formal language kind of concept, talking about languages, but that's just a way of formalizing all kinds of computations. So we really could be talking about computing functions or whatever else, drawing pictures. So don't get fooled by thinking that this is just a theory about these abstract languages and it's got no connection to reality. It's just a way of formalizing what computations are about. Here we recognizing languages. So this is really saying, well, if a Turing machine is like an algorithm, and this is like an algorithm, and then algorithms get written as programs, this is the same kind of question of whether two programs do the same thing, or do two algorithms do the same thing. And that's definitely an important thing you want to know. If you have a whole bunch of software, 10 million lines of software, which that really exists, and then you fiddle with it, or now you have 12 million lines of software, whatever. You want to know if they do the same thing, or if one does more, or whatever. All these kinds of questions are really quite relevant. And you can't sit there as a human and look at the two programs and decide. And testing specific input, of course, if you find specific input where the two programs behave differently, then you have your answer, they're not the same. But if they perform the same on all the test cases that you give it, that still doesn't tell you for sure that they really are producing the same results always. So you would like to have a computer do that work for you. You'd like to have a computer be able to look at these two programs, or two algorithms, or two Turing machines, and say yes or no that these two languages are the same. And what this is saying is, sorry, not going to happen. Okay, there is no Turing machine that can do that. And that doesn't stop people from trying, because it's a very practical question, and you may put together a program that does a good job at catching two algorithms that are not identical, or gives you some high sense of confidence that the two algorithms will behave the same over input that you're likely to see in practice. But if you're guided, if you as an algorithm designer want to come up with an algorithm that absolutely is provably correct for this question of whether two languages are identical, and you're struggling to get that algorithm and a proof that it's always right, you're going to fail. It's just not possible. And that's what this is saying. Okay, well, let's prove it. We're going to reduce. Well, we can reduce. Now we have a repertoire of problems that are known to be undecidable. We can use any one of those to reduce to this language, and therefore proving that this language is undecidable. So far, all of our reductions have come from ATM. And ATM is a particularly nice, expressive language that makes reductions particularly easy. A lot of people use it, but we don't have to use it, and this is going to be a case where we're going to use ETM. Right there, ETM. Reduce ETM to EQTM. Okay? ETM, again, it's the set of all descriptions of Turing machines such that its language is empty. Does anybody see how the reduction should go? Anybody suggest a... Do what? Build a machine that simulates M1 and M2 and feed that into ETM. I'm not sure. Well, ETM just takes in a single machine. I'll give you a hint. This is probably the easiest reduction we'll see. So when you see it just right, it is particularly simple. Okay, so again, let's build our boxes. We'll start with our box. So reduce ETM to, okay, so suppose, I guess I'm not quite ready for the box. Suppose EQTM is decidable. So that means, there's my chalk. Oh well. It means there is a Turing machine R that decides EQTM, and we want to use that one to decide ETM. Okay, so now we can draw our picture just so we are clear on what we're trying to do. So here's the box for H, and H is supposed to be a decider for ETM. Okay, and what's the input to ETM? What's the input to this box to H look like? Yeah, it just takes in descriptions of Turing machines. Okay, and then of course we know this is we need an accept and a reject, and we know inside here we're going to have this R, the supposed R, which can decide EQTM for, okay. EQTM. So what we have to figure out is what is H doing inside here to be able to feed something in to R. And what does R get as its input? It gets two machines, right? Description of two machines. It gets an M1 and an M2. So we have to figure out how H takes in M and then creates a description of two Turing machines, M1 and M2, such that when R looks at those two Turing machines and decides the equality question or equivalence question, then its accept or reject can be used to accept or reject M. Okay, now I don't know whether an accept here is going to be accept there or it's going to be reject creates an accept. We've seen these different ways. So we'll just leave the picture like this and then fill in the details. Now can anybody suggest a way to do this? Okay, well, I'll tell you. So H creates a description of a Turing machine M1 that rejects everything. All right? So L of M1 is empty. M1 just rejects everything. So let me ask, do you think that do you think there's a Turing machine H that can create a description of a Turing machine that just rejects everything? Yeah, that's a pretty simple one. Okay? So certainly H can create a description of such a Turing machine. It doesn't even need to look at M. You know, we can have that hardwired into H, the particular Turing machine that rejects everything. And that's what M1 is going to be. All right, now it's got this oracle R. Sometimes these supposed Turing machines we'll call oracles, you know, like the Oracle of Delphi. But at any rate, this magical supposed Turing machine R that can decide the equivalence question. But what we want is to build a Turing machine H that is deciding the ETM question, that is whether or not the language of a particular Turing machine is empty. So, anybody have suggestions for this? M and M1. Okay, yeah, you could do that. It seems more parsimonious to describe it as M1 and M, but the same thing. So, yeah, so what happens here is what gets fed into this oracle R, this Turing machine R, is going to be M and M1. Okay? Well, certainly Turing machine H can create a description of M because the input is a description of M. And Turing machine H can create this M1, we just argued that. Now R takes a look at these two languages and decides yes or no, they're equivalent. Well, if they're equivalent, because the language M1 is the empty language, the only way they're equivalent is if M is also the empty language. Okay? So when R accepts, meaning these are the same, then that means that M is the empty language, which means that should be an accept. That goes that way. And when R rejects, that means that these two languages are not equivalent, but L of M1 is the empty language, which means that L of M is not the empty language. Okay? And the way this was phrased, you want to accept if it is the empty language, you want to reject otherwise. So you do that. And now we have a description of a Turing machine H that can decide ETM, provided that there's a Turing machine R that can decide EQTM. Since we know that ETM is undecidable, it then follows that EQTM is undecidable. Okay? H creates a description of Turing machine M that rejects, and then inputs M, M1 to R. H accepts if R accepts, rejects if R rejects. Okay. So H is a decider for ETM, or H would be a decider for ETM if R exists. But ETM is undecidable, so R doesn't exist. There is no such R. R can't exist. So EQTM is undecidable. Okay? So this is the kind of question I might ask on that mini midterm, which is, it's a closed book exam. So I could just say, show me the details of reducing ETM to EQTM. And if you understand them, if you understand all this, even if you don't just absolutely memorize it one line at a time, you should be able to recreate it and walk yourself through it and write that down during the exam. So the exam would probably have a couple of these kinds of questions. One might be decidable question, the other undecidable question, with a reduction or maybe something about diagonalization or self-reference. But being closed book and being a half an hour, I'm just going to be basically asking to see if you've absorbed this complicated material as opposed to trying to think through something that you haven't seen before, which would, I think, be very, very hard to do in an exam setting. Okay. Now the next one that the book does is an interesting one about whether there's a Turing machine that can take a look at another Turing machine and decide if that second Turing machine only accepts a regular language. Okay? I don't understand the way the book does it. I wonder if there isn't an error there. I stared at that thing for a while. So I'm going to try to do it differently and sort of off the top of my head. So this is dangerous. This is really, should never try. Just like they say for lawyers in court, you should never ask somebody on the stand a question where you don't already know what the answer is going to be, because it could go all kinds of weird ways. But I did think about this on the way walking over here, so hopefully that'll work. Okay, so, and then after we hopefully understand it the way I do it, maybe we can all take a look at what's in the book and somebody can explain to me how what's in the book does it. Yeah, okay, so the statement of this problem is regular it's the set of Turing machines such that L of M is regular. Okay, so this is a property of this language. We've studied regular languages. A language is either regular or it's not. And in fact, we know some techniques for proving that a language is regular. We can either build a deterministic Turing machine, a deterministic finite state machine, or a non-deterministic finite state machine, or a regular expression. And all of those demonstrate that the language is regular. And to prove that it's not regular, we have some techniques for that. The pumping lemma was well, that's the one that we studied in this class. So here we want to say, can we build this box that can get rid of us? I mean, as I say, we can look at a language and think about whether it's regular or not, and sometimes succeed in showing that it's regular, sometimes succeed in showing it's not regular. But here we want to automate that. We want to build a Turing machine which takes in, well, the description of some other Turing machine, which is doing some computation, and deciding whether that the language that's accepted by that Turing machine is a regular language or not. Okay? Okay, so okay. So one idea, I guess I've erased it, but we had a language previously, halt, right? Halt is MW such that M halts on W. And we already know this is undecidable. We already did that. That was last time, but I wrote it up again this at the beginning of this hour. So we want to prove that regular, I'll just abbreviate it as regtm, is undecidable. And the proof is going to be reduce halt tm to reg. Okay. Yeah. Okay. All right. Let's draw our boxes so we can kind of get our wits together. So we're reducing halt to reg. So that means that we want to build a Turing machine H that decides halt. And inside, we're assuming we have a Turing machine R for reg. Okay, and then accept or reject. And the input here is, since this is going to be a decider for halt, what's the input look like? Yeah, it's the same as the input in the language halt, or what the strings look like in halt. And then what's the input here look like? Yeah, just a single Turing machine. Now I don't know whether it's that Turing machine, so I'm just going to call it M1. Okay. And then we have to describe what goes on in here to take in M and W and create an M1 such that when R decides whether M1 is regular or not, that decision can be used to accept or reject the input MW for the halting problem. Okay? So what we want is we want to describe, or we need to describe how H creates a Turing machine, Turing machine, a description of a Turing machine M1, so that when R decides decides whether or not LM1 is regular, that result can be used to decide whether or not M halts on input W. So everybody see the game plan? I think it's very useful to write out this kind of game plan of what are we trying to accomplish. It's useful to write this kind of a picture which gives you the basic organization, and then write out what it is that we want to accomplish inside here. And then you can start focusing on the details. But if you just take this problem and just let your mind start going, until you get good at it, you just don't know where to begin. What are you supposed to be doing? And you thrash at details instead of seeing it in a nice progression. And of course, then ultimately, as you get good, or if you're among experts who've been doing this for a while, all they have to do is say a couple of keywords, and everybody knows what they're talking about. That's just a couple of keywords that I'm stalling for time here. It's like tuning jokes before the concert. Okay, so, but no, everything I was just saying is important. But now, what is the details here? Let me make this picture a little smaller so I have room to write the details. Okay, so that's the description of what we want to do. So I think the following thing might work. H is going to create this Turing machine M1, and what does M1 do? M1 simulates M on input W. Okay? Well, certainly H can create a description of a simulator for M on W. That's the universal Turing machine. So the universal Turing machine can take an M1 on W. That's what it should do. And if the simulation halts, okay, if the simulation halts, then what do we want to do? M1 uh-oh. Let me look at my little scratchings here. Okay, it's not going to help. Okay, we got to think. So M1 is going to simulate M on input W. Now what can happen is that M either halts or it doesn't. Okay, so if it halts, then what? Uh-oh, M1 simulates M on input W.
I think you want regular TM to be deciding whether it halts or not, or determining whether it halts or not. Because you know, like, regular language will always halt. I think that's the information you need to use.
Okay, let me back up and tell you a little bit how we're trying to do this. So we're going to try to distinguish. We want R. We want R to distinguish whether LM1 is empty actually, let me put it the other way around. We want L of M1 to either be empty or 0 to the n, 1 to the n. Okay. The empty language is regular, right? So that's a language that's regular. 0 to the n, 1 to the n, we know that's a language that's not regular. Okay? So based on whether M halts on W or not, we want M1 to either be the empty language, L of M1 to be the empty language, or we want it to be this one. Okay. Okay. So M1, we're building this, H is building this machine M1. And what does M1 do? M1 simulates M on input W. Okay? And if the simulation halts, then M1 takes in its input. Okay, remember, the input to this big box, to H, is the Turing machine M and the input W. Okay? So H can build a Turing machine which already has in it the knowledge of W. And it can simulate M on W. But it hasn't even looked at its input yet. M1, when it's doing this, hasn't even looked at its input. Okay? Its input, I'll call it X. Or maybe call it W1. Okay? So after M1 simulates W, if it halts, then M1 takes in its input W1. Okay? Well, what's W1 going to be? So H takes in its input W1. Okay. And then M1 accepts if and only if its input W1 is of the form 0 to the 1, 0 to the n, 1 to the n, for some n greater than or equal to 1. Okay. Now, a Turing machine, this is not a regular language, but a Turing machine can definitely look at a string and find out whether it's an equal number of zeros followed by an equal number of ones. Even a PDA can do that. So this is a rather trivial thing for a Turing machine. So definitely H can create this Turing machine M1, which does the following thing. M1 simulates W, but W is known at this point, so H can create a Turing machine, a description of a Turing machine that simulates that. And if that simulation actually halts, then what M1 does next is it actually looks at its input, W1. And M1 will accept if and only if W1 is of that form. Okay? Otherwise, it just rejects. Okay? All right. Now let's analyze this. Let's look at, I hope this is going to work. You don't think it's going to work?
So otherwise the simulation of M1W never halted.
Yeah, no, but
So we won't reject, we'll just never halt.
right. But here I'm talking about what M1 does. M1
Oh, okay, sorry.
rejects. That's under this if it halts. Okay. Okay, so now let's look at the behavior. Let's look at what happens in H. Okay, let's look at the behavior of the whole system here. Sorry, let's look at M1. Okay. So what does M1 compute? Well, accept. What does M1 accept? There are basically two possibilities. They're not just single strings anymore, but they're two types of languages that it can accept. What are they?
The empty language?
Yeah. So M1 might accept the empty language, and that's if and only if what? M does not halt on W. Okay? M does not halt on W. If M doesn't halt on W, then it doesn't accept. It doesn't accept anything. Okay, M1 doesn't accept anything because it's spinning its wheels forever. Okay? What else can M1 possibly accept? Yeah, it accepts strings, well, of the form 0 to the n, 1 to the n. Okay? And that's if and only if M does halt on W. Okay? And that's all it can do. It can either accept nothing or accepts strings of that form. Yeah?
I'm not confident you could generate M1 with a Turing machine.
Okay, so yeah, we're describing what we want H to do. H creates an M1 that does that. Now, M1 is certainly we can describe M1. M1 simulates M. We have that on input W. We know how a simulator works. That's the universal Turing machine, and we know what it means to halt. Okay, so if it halts, then M1, this is a description of what M1 would do after this simulation halts. M1 would then finally look at its actual input, W1, and when it looks at its input, it would accept, if and only if W1 is of that form. That seems doable. The Turing machine can take a look at a string and decide if it's of the form 0 to the n, 1 to the n. If it is, then it's going to accept. Otherwise, it's going to reject. But your objection is, can H create a description of M1? H is a Turing machine. This is the description that we humans came up with. But can a Turing machine create the description of that? Well, it's got M, it's got W. Okay, so it can, and we know about universal Turing machines, so it can create the universal Turing machine that simulates M on W. I think we've done those details. And then it adds to that, if that universal Turing machine has an accept or reject. Okay? So from the accept state or the reject state, that's when it knows that it's halted, and so it's going to add on to that transition rules which say, okay, now take a look at the input to M1 on its tape, and M1 will accept if W1 is of that form, so it has to build in the rules for a Turing machine looking to see if its input is that form, but that's pretty simple. And otherwise it rejects. Are you convinced? Okay, good. All right, proof by acceptance. Okay, good. So we've got this. Now, M1 might accept strings of this form, but that's the only strings that it can accept. Otherwise, it's accepting just the empty language. So L of M1 equals that, or L of M1 equals the set of 0, 1, 0 to the n, 1 to the n greater than or equal to 1. And this one is a regular language. And this is a non-regular language. Right? So this Turing machine H has created a description of a Turing machine M1 where either the language M1 is a regular language, or, well, this is a tautology, the way I'm saying it now. The language of L of M1 is either a regular language or not. But in particular, L of M1 is regular if and only if L of M1 is empty, and L of M1 is empty if and only if M halts on W. So if and only if M halts on W. Okay? Oh, doesn't halt, sorry. M doesn't halt. Okay, and it's non-regular if and only if M halts on W. Okay? All right, so given that, how do we connect these? What do we want? If R, which after all is now the supposed Turing machine that can decide whether the Turing machine it's given produces a regular language or not, accepts a regular language or not, if it's regular, that means that M does not halt on W. So this should be accept goes to reject. And if R decides that the language is not regular, that's because M halted on W. So a reject here should be an accept there. Whew, we did it. Okay, sorry for the hesitation there. So I think this works. And I think, well, I can't understand what somebody should help me read the Sitzer's description of how one can do this reduction to show that the reg TM is not decidable, because I'm somehow not understanding it. Maybe it's really the same thing as this. I certainly picked up some keywords from what he wrote there in creating this, but I just don't see it. At any rate, but this is a proof that reg is not decidable. Okay, so I think that's going to be the end of the undecidable languages we're going to look at, except for the ones in your homeworks. Now I want to say a little bit more. We have 4 minutes left about the next little piece in the book, and it tries to formalizes what a reduction is, and in so doing explains that all what we've been talking about is actually broader than just accepting or rejecting, recognizing or deciding languages. We're really talking about functions. And so we all know what a function is. You've seen functions since grade school. So input is x, and this computes a function of x, for example, x squared over 3. Okay, so in comes x, out comes a particular value, and that's a function. Okay, lots of functions. Now, a Turing machine accepts strings or rejects strings or doesn't. It could perhaps not halt. And how do we think about a Turing machine as actually computing a function? We can think of it in a couple of ways. We could have a language where the input is x, f of x, and the Turing machine has to decide if f of x, if what, well, maybe I should do it this way, x, x prime, and the Turing machine decides if x prime is equal to f of x. Okay, so this is a Turing machine that's supposed to basically be computing the function f. It's and so then we can say, well, is there a Turing machine that can take in an x and an x prime and decide if x prime is in fact equal to f of x? So that is nicely consistent with our notion that a Turing machine either accepts or rejects. But we could relax that a little bit, and we've actually seen an example when I was enumerating, when a Turing machine was enumerating binary strings. We described a Turing machine which at one intermediate part of its computation was writing binary strings on its tape. But we didn't have the formalism to say that was going to be the end result of what the Turing machine does, because Turing machines are supposed to accept or reject. So we had something else on top of it. But now we can relax the idea of a Turing machine if we want, and just say that the Turing machine takes in x and leaves, when it halts, f of x on its tape. Not a big stretch. Of course, it means that the Turing machine has to halt, okay? And when it halts, it leaves f of x on its tape. Now, we know lots of functions, x squared over 3, all kinds of other functions. Question is, is there a function f? I mean, it's a perfectly well-defined function. You take in the input, you get a result out, function f, such that there is no Turing machine which can compute f of x. And what does it mean to compute? Here it means this. So Turing machine M computes f of x if M takes in x and writes ultimately f of x. Okay? So we've seen some Turing machines that do exist. We know how to take in two numbers, and the Turing machine can create the sum of those two numbers. We've even seen how it can take the product of two numbers. And you hopefully, your intuition about Turing machines is advanced enough that you can see how a Turing machine can implement other functions. But can Turing machines compute all possible functions. Okay, so we run out of time, but I'll examine that question next time.